This is the complete video on set theory. Here you will find all the topics related to set theory in one video. So let's continue. Before continuing, please subscribe and share this channel with your friends. What is a set? The definition is a set is a well-defined collection of objects. Let us give an example. If I say A is a set of all natural numbers less than 10. So we have A is a set containing the natural numbers less than 10. So we have 1, 3, 5, 7, 9. So what we do here, we write the elements within the curly brackets, and elements are separated by commas. Okay, here the order does not matter. If I write A is like this, 1, 3, 7, 5, 9. So order does not matter, but it should be a well-defined collection. By well-defined, what we mean, we say a given collection of objects is well-defined if we can definitely say whether a given particular object belongs to the collection or not. Here you can see I am saying 3 belongs to set A. 3 is an element of set A. So it is true for me, for you, for any person. Why? 3 is an element, 3 is an odd natural number less than 10. Likewise, 5 shares the same property that 5 is odd natural number less than 10. This also shares the same property. 7 is odd natural number less than 10. So there is no ambiguity here. Okay, what is true for me is true for you, a person living in India, Canada, USA. For all persons, it is true. Okay, so if I write this example here. Now let's take another example. Let us say we have B is a set or the collection of all vowels in English language. So we'll have A, E, I, O, U. This is also well defined for you or me. This is true. A is a vowel, E is a vowel. So there is no difference of opinion. This is what we call the well defined. So let us see what is not well defined. If I say, let us say the collection of all rich person in the world. So this is not a set. For me, a person having, let us suppose, an annual income of $10,000 can be rich, but for you can define him as poor. Okay, for underdeveloped countries, a person earning $10,000 per year can be rich. For developed countries, it can be poor, the same person who earns. So there is ambiguity. We cannot define perfectly what is rich and what is poor. Likewise, we can say the set of all honest persons. This is not also a set. Why? Because a person can be honest for me, the same person would be dishonest for me. So we cannot define the honesty here. Likewise, when we say the collection of all famous football players, that is not the famous persons in the world or football players in the world. Likewise, when we say the collection of all beautiful, girls in a class. So this is also a vague statement. What I consider beautiful, you have other opinion there. Okay, you will not consider her beautiful. So there is ambiguity here. We say a set is well defined. A given collection of objects is said to be well defined if we can definitely say whether a given or particular object belongs to the collection or not. How to specify the sets? There are two methods of describing the set. One is the rooster form, another one is the set builder form. Now in a rooster form, what we do, we list all the elements of a set, enclose them within curly brackets and separate the elements by commas. This is called the rooster form. Now in set builder form, what we do, set builder form describes the properties of a set using a rule or a property that defines the membership. So if I have this rooster form, how do I define it? So let us see what is here. So we have A is a set of all natural numbers which are between 1 and 5. Okay, so 2, 3 and 4, these are the natural numbers. And how do I write it in the set builder form? So we write it like this. So we have A is a set, then we take curly brackets, we define the variable x. So we say the set of all x such that, now what is the rule here? So rule is that x belongs to natural numbers. Okay, so we have to define here. So x belongs to natural number and x lies between 1 and 5. So we can write it like this: x is greater than 1 but less than 5, and we enclose it with the curly brackets. Okay, so given this rooster form, we have converted it into the set builder form. Okay, so what did we do here? And if I write it, if I explain this notation here, so it says us the set or we can say set A is a set of all x's, okay, all x's, such that x is a natural number, so n denotes natural number, and x lies between 1 and 5. So the meaning of this is that we have x which is greater than 1 but less than 5, so we will have numbers 2, 3 and 4. Okay, so the thing is to say that first we define variable, and then we describe the properties or conditions. Okay, so let us take another rooster form. Let us suppose we have a set which contains the vowels. So we have A, E, I, O and U. So this is in the set builder form, so we can write it into the, sorry, this is in the rooster form, we can write it in the set builder form like this. So A, set A contains, so we can write it like this, all x's such that, so this vertical bar means such that x is a vowel. Okay, so we have to specify the rule here. Then we can take many examples, but here I have given you an idea how do we write the sets in rooster form and set builder form. In rooster form, we list all the elements of a set, separate them by commas and enclose them with curly brackets. In the set builder form, what we do, we define the set, okay, and we write it in the rule form or in a rule method. By rule method, or whatever we mean, so we define some properties in the set builder form. So the element is described by the rule or property. So to cut it short, the set builder form describes the elements of a set using a rule or a property. So property is here x belongs to natural numbers and x lies between 1 and 5. Here the property is x is a vowel. Let us take some more examples how to convert a roster form in set builder form. Suppose we have a set in roster form like this. A is a set containing elements 1, 2, 3, 4. So this is in roster form. In the roster form, we list all the elements of a set, separate them by commas, and enclose them with curly braces. This is roster form. Now we need to convert this into set builder form. So what is a set builder form? So in set builder form, what we do, we describe a set by specifying the properties that its members must satisfy. Let us suppose we have a set A, and I will explain all the things here. Now what I have written here, so let me write it like this. So this shows us the name of the set. Name of the set is A. So x, these are the elements in A, elements in set A. Then we have the condition for x to be in this set A. So this is a condition for members x to be in set A. Okay, so how do we pronounce it? So we can say that A is a set of all elements x. We call this such that, in this vertical line, such that x satisfies the conditions. Okay, so we have the different kinds of conditions on x. So how do I write this in the set builder form? So we can write A is equal to, if we see these are all natural numbers and they are less or equal to 4. So can I write, this is a set x, the set of all x's such that, the set of all x's such that x is less or equal to 4. Okay, we have, but we have to specify and another condition, that is, and x belongs to natural numbers. Okay, so this is how do we write this rooster form in set builder form. We can write it in another way also. So there are 2-3 methods. So we can write it like this also. A, the set of all x's such that, if we show this vertical line by this colon symbol, so we can write it in this fashion also, and x belongs to natural numbers and x lies between, so x lies between 1 and 4. So we can write it in this form also. Okay, so let's take another what we call a set. Let us suppose we have a set B in the roster form. Let us take numbers. Let us say we have 1. So let me take numbers Okay, so let us take a simple example. Let's say we have 3, 6, 9, 12. Okay, this is in rooster form. How do we write it in set builder form? So here we can see these are all multiples of 3 here. Okay, so can I write it like this? B is a set or the set of all x's such that x is equal to 3n. Here you can see if we put 3 n is equal to 1, so we got 3 1s are 3. Then if n is 2, we get 3 2s are 6, 3 3s are 9, and 3 4s are 12. Okay, then we have to specify another condition, that is n is less or equal to 1. Sorry, n is greater or equal to 1 but less or equal to 4. Okay, so what does this mean? So when we plug n is equal to 1, we will get, so let us see here, when n is equal to 1, we will get the first element is 3 into 1 is 3. When n is equal to 2, n is equal to 2, we will get 6. Likewise, when n is equal to 3, we will get 9. N is equal to 4, we will get 12. Okay, in rooster form if we write it here. So the set of all x such that x is equal to 3n, because these are the multiples of n, and n lies between 1 and 4 inclusively. That is, we include 1 and 4 here. Okay, now let's take another let us say we have set D in rooster form like this. We have let us take the squares in this time. Let us suppose we have 2, 4, 8, 16 and 32. Okay, this is in rooster form. So how do I write it in set builder form? Here you can see this is actually 2 square, 2 cube, 2 raised power, sorry, we have 2 raised power 1 is 2, 2 square is 4, 2 cube is 8, 2 raised power 4 is 16, 2 raised power 5 is 32. Okay, so can we write it like this? D is a set, or we can say the set of all x's such that x is equal to 2 raised power n. Okay, so when n is equal to 1, we will get 2. When n is equal to 2, we will get 2 square, which is 4. Okay, then we have to satisfy also specify another condition, that is n lies between, and let me write it here, where n lies between 1 and 5 and n belongs to natural numbers here. Okay, now let's take another example. Let us suppose we take the numbers. Let us suppose we have a set S which is equal to -6, let us say -4, -2, 0, 2, 4, 6. Okay, let us see what is happening here. So these are all multiples of 2 here. Okay, but we have negative numbers also here. So can we write it in the set builder form like this? So we can write the set of all x's such that x is equal to 2 times n, 2 times n here. Okay, now what is n here? So we have here, if we can see, 2 into -3 is 6, 2 into -2 is 4, 2 into -1 is -2, then we have 2 into 0 is 0, then we have 2 into 1 which is 2, likewise we have 2 into 2 is equal to 4, and 2 into 3 is equal to 6. Now here obviously we have, for n we have -3, -2, -1, 0, 1, 2, 3. That means we can write it like this, where n belongs to the integers, because in integer we take positive numbers and negative numbers also. So here n belongs to z, not n. Then we would have only the positive numbers, because we have negative numbers here and we have sets. We saw here that we have negative numbers and positive numbers obviously here. And what is another condition? There is this n lies between -3 and +3. Okay, so these were the examples how do we convert rooster form in set builder form. Now let us see the types of sets. First we have null set, or what we call the void set. So what is a null set? It is simply a set with no elements at all. It is denoted by the symbol phi, or we denoted by the curly braces with no element in it. Okay, so let us give an example. So if I say we have A is a set, okay, which contains all x's such that x is an even prime number greater than 2. So what will be the elements in set A? So we know the even numbers start from 2. So first even number is 2, then we have 3, then 5, then 7, then we have 11, then 13, and so on. These are all what we call prime numbers. Since we have to find out the elements in the set where we have even prime numbers greater than 2. So the prime numbers greater than 2 all odd. They are all odd. Okay, so in this set we will have no element at all. Okay, because there is no prime number greater than 2 which is even. So A will be a null set here. Okay, this is an example of null set. Then let us take another type of set, what we call the singleton set. So a set containing only one element is called a singleton set. Containing only one element. Let us suppose we have a set A and we have only one element here. Let us suppose this as, let us take L. So we say this is a singleton set because it contains only one element. Okay, then we have another type of set, what we call the finite set. Okay, so a set with limited or countable number of elements is called a finite set. So we can write a set with limited number of elements or countable number of elements is called a finite set. So if I take an example, A is a set, let us suppose such that A contains all x's such that x is prime number less than 10. Okay, so let us see what will be the elements in it. So first prime number is 2, then we have 3, then we have 5, okay, then we have 7. Okay, so this we can say, since we can count the number of elements here, this is a finite set. Okay, then let us take other sets also. Then we have infinite set. So it is very simple. A set that contains unlimited number of or uncountable number of elements. You know, a set containing unlimited or uncountable number of elements. For example, we have a set, which contains the natural numbers. So we have 1, 2, 3, the set of all natural numbers. Then we have and so on up to infinity. So we cannot count all natural numbers. So this set will be called an infinite set. So we can also write it like this: A is a set A contains all x such that x is or x belongs to natural numbers. Okay, if we have this condition, so we have the natural numbers and there is no restriction on the number of elements in it. So this is an infinite set. Simple. Then another type of set is what we call, let us take, or let me rub this out first. So then we have equal sets. Okay, so two sets are said to be equal. Let me write it here. Two sets are said to be equal, okay, if they contain exactly same number of elements. Okay, so exactly same number of elements. By this what we mean, if we have a set A which contains numbers 1, 2 and 3, Then we have another set B which also contains let us suppose 2, 3, 1. Here order does not change. Since the number of elements in both the sets are equal and we have same elements in both the sets, we say set A and set B, these are equal sets. Okay, so here we have 1, 2, 3, here we have 2, 3, 1. So order does not matter, we say these are equal sets. Okay, two sets are said to be equal if they contain exactly same number of elements. Why I am stressing on this exactly same? Let's compare it with the equivalent sets. Sorry for the spelling mistake if I have here. Equivalent sets. Okay, now what are equivalent sets? We say two sets are equivalent, and let me write it here. Two sets are equivalent sets if they have same number of elements. Number of elements, regardless of what the elements are or what those elements are. Okay, if two sets have same number of elements or equal number of, or let me put it like this, same number of elements regardless of what those elements are. If I take a set, let us suppose A is a set which contains number 1, 2 and 3. Then I have another set B which contains, and let us suppose 5, 6, 7. We say these two sets are equivalent sets. Okay, if we, or regardless what the elements are, if the number of elements are same, they are equivalent. Okay, it does not matter what elements are those, the only condition is that number of elements should be equal. Or if I take here to make it more understandable, so let's take A, B and C. I am saying that A and B are equivalent sets because they have same number of elements here, and we do not care about what those elements are. Okay, unlike in case of equal sets where the number of elements should be equal and the elements should be same. Okay, so let me wrap this out. Then we have overlapping sets. Overlapping set. So we say two sets or set containing, let me write it here, sets containing at least one common element. So if I have set A, let us say 1, 2, 3, I have set B where I have 1, 2, 3, 4. If two sets have at least one common element, here we have two common elements. Okay, it doesn't matter, at least one common element should be there. Then we say that sets are overlapping sets. Here I can say A and B are overlapping sets. Okay, now then we have disjoint sets. So it's opposite, that is sets, let me write it here, sets which have no common elements. Let us suppose we have a set 1, 2, 3, another set is B which contains 5, 6, 8. Okay, these two are disjoint sets because they have no common element. Okay, so let me wrap this also. Then we have proper subset. Okay, and improper subset. So let us first define proper subset. We say, let's take two sets. I am saying set A is a proper subset of set B. Okay, if all elements of set A are also in set B and there is at least one element in B in set B which is not in set A. Okay, so by this what we mean? So let me take an example to explain it. Let us suppose we have a set A where we have elements 1 and 2, and I have another set B where we have 1, 2, 3 and 4. Okay, in this case I say that set A is a proper set of B. Okay, if set B contains all elements of A and set B has at least one element that is not in set A. Here you can see set A has elements 1, 2, B has also elements 1, 2, so all elements of A are in this set B, but there are some elements in B which are not in set A, so we denote it by A, then we use this symbol B. We say A is a proper set of, subset of B. Now what about improper subset? So let us explain it here. Improper subset. Now we need to define the improper subset, and let me write the definition. We say set A is improper subset of set B if all elements of set A are also in B, and A is equal to B. So by this what we mean? So if I take a set, we have 1, 2 and 3, and I take another set where I have the same number of elements and same elements, obviously. In this case I say A is a proper subset of B because B contains all elements of A and also A contains all elements of B. So in this case we say A is a proper subset of B. So it is denoted by A by this symbol. Okay, so here we can say that A is, because here we have set A contains, rather set B contains all number of elements which are in set A, or we can also say here, and here we have also B is a subset of A. Okay, so we say set A is improper subset of B if all elements, here you can see, of A are also in the set B, and A is equal to B. That means number of elements in A are equal to number of elements in B. Okay, so now this symbol is exclusively, if we write this symbol is exclusively used for showing proper subsets. Okay, proper subset, while as this symbol represents any subset, okay, including the improper set. Okay, so this is the difference between this symbol and this. So this is exclusively used for showing the proper subset, and this symbol is represents any subset, okay, including the improper subset. Now let us discuss about the power set. A power set is the set of all possible subsets of a given set. Okay, let me write it here. So power set is the set of all possible subsets of a given set. Okay, let me explain it with an example. Let us suppose I have a set A which contains elements 1, 2 and 3. Okay, power of set is denoted by PA. So P denotes power, A is the name of the element. So power set is the set of all possible subsets of a given set. Okay, so what will be the sets here? So first we will have 1. 1 will be the subset of this. Obviously 1 is the subset of the given set, so let us write it here, 1. Then we will have 2 is also the subset of the given set. 3 is also the subset of the given set. Then 1, 2, this is also the subset. Likewise 1, 3. 1, 3 is also the subset of the given set. Then we have 2, 3. 2, 3 is also the subset of the given set. Now if I write, let us suppose we have 2, 3, or if I write 3, 2, to write 3, 2 or 2, 3, it is same because order does not matter here. Okay. Then what we include in the power set? We include the empty set, what we call the null set or void set, and we also include the given set itself, that is 1, 2, and 3, because given set is always a subset of itself. Okay. Then let us enclose it by the curly braces. So this is what we call the power of a set. The set of all possible subsets of a given set is called the power set. Okay. Now how do we see, or how do we identify the number of elements in a power set? Okay. So I will be explaining that very thing also here. That is how many subsets. To find out that very thing, let us first define the cardinality. Cardinality of a power set. Okay. Now cardinality of a power set gives us the number of subsets in a power set. Okay. It shows us number of elements or subsets in power set. Okay. In the given example, and how do we find cardinality? So cardinality is denoted by this absolute symbol, modular symbol. So P denotes the power, A denotes the name of the set. This is the cardinality of a power set. It is equal to, so to answer the question how many subsets will be in a given set is called the cardinality of the power set. It will be equal to 2 raised power n, where n denotes the number of elements in a given set. So let us take the given example. So we have 2 raised power. How many elements are here? 1, 2, and 3. We have 2 cubed, which will be equal to 2 to the 4 to the 8. That means the number of elements in a power set will be equal to 8. What we call the cardinality of a power set. Now let us count 1, 2, 3, 4, 5, 6, 7, and 8. Okay. Let us take another example. Let us suppose I have a set B, which contains elements x and y. Now first thing is, what will be the power set of B? Power set of B will be equal to the all possible subsets of the given set. So first we include the empty set or phi. So we can denote phi. We can denote it by empty set by phi or this symbol. So I take phi here. Then we will have x. Then we will have y. Then the given set. These are all the subsets of the given set. Now this denotes the power set. Now how many cardinality of the power set B will be denoted by this symbol. It is equal to 2 raised power n. Here we have 2 elements, so we have 2 square. That means we will have 4 elements. So how many subsets are in a given set? That's called the cardinality of a power set. Likewise, we can take another example, or let us take an example. Let us say C is a set which contains numbers 1, 2, 3, 4. Now how many subsets will be in this set? It will be equal to 2 raised power the number of elements 1, 2, 3, 4. So we will have 16 elements or 16 subsets. That is, the power set of this given set will have 16 subsets or elements. Okay. Likewise, if we have let us say S is a set which contains 8 elements. Therefore, number of subsets in the given set will be equal to 2 raised power 8. Okay, that will be the number of elements. Now let us learn how many proper subsets are in a set. Suppose we have a set which contains elements A, B, and C. Now the subsets of the given set will be, so phi is always a subset of any set, so phi is one set. A is also the subset of S, B is subset of S, C is subset of S, AB is also the subset of S, AC is also subset of S, BC is also subset of S, and the given set itself is a subset of a set. Okay, so what I can say here, that a set is a subset of itself. Now number of subsets in a set S, it is equal to 2 to the power n, where n denotes the cardinality of the set. Cardinality is simply the number of elements in a set. So number of subsets will be equal to 2 to the power 3 because the number of elements in the given set is 3, so which will be equal to 8. And here we can count them 1, 2, 3, 4, 5, 6, 7, 8. But we need to find out the number of proper subsets in S. Okay? Now, what is the definition of a proper subset? We say proper subset is a subset that does not contain all elements of the original set. Let me give you an example. I have explained it in earlier videos. So let us suppose we have a set A which contains 1, 2, and 3. And we have another set which is 1 and 2. And we have another set C which is 1, 2, and 3. Now here I can say B. B is proper subset of A because B does not contain all elements which are in set A. Okay, here we have 1, 2, 3 elements, here we have only 2 elements, so I can say B is proper subset of A. But C is in fact the improper subset of A because the number of elements in C are equal to the number of elements in A, so C is improper subset of A, B is proper subset of A in this case. Now let us see here in this example. So 5 is proper subset of S because it does not contain all elements of the set S, because 5 we have empty set is always a set of any set, always a subset of any set. Now A is a set and we say A is proper subset because A set, rather the elements in this set A are less than the elements in set S. Okay, so simple thing. Since we have to find out the proper subsets, how many proper subsets will be in the given set, so it will be equal to 2 to the power the number of elements in a set minus 1. So we have to exclude this set because it is improper set here, improper subset. So it will be equal to 2 cube minus 1, which is equal to 8 minus 1. So we will have 7 proper subsets. Okay, so let's take another example. Let us say we have a set A, it contains X and Y. Okay, now the subset is, now what will be the subsets here? So 5 is always a subset, X will be always a subset of A, Y is also the subset of A, and XY, the given set, is itself the subset. Okay, so how many subsets are here? 1, 2, 3, 4. So we can write it like this: 2 to the power n, since n is equal to 2, so we will get 4. So number of subsets in a set is equal to 2 to the power number of elements in a set, which is 4. Now how many proper subsets? So this is proper subset, this is also proper subset, this is also proper subset, but this is not proper subset because it has same number of elements which are in the original set rather. Okay, so this set is improper, so we exclude this very set here. So proper subsets will be 2 to the power n minus 1, which will be equal to 2 square minus 1, which is equal to 3. So here we can see 1, 2 and 3. Here there are 3 subsets. Okay, rather 3 proper subsets, and total number of subsets is equal to 4. So we always subtract 1 when we count the number of proper subsets when we apply this formula, that is 2 to the power the number of elements. Now let us learn about the number system. First we have natural numbers. Natural numbers are denoted by symbol n. Natural numbers start from 1. We also call them counting numbers. Then we have 2, 3, and so on. These are called natural numbers. Then we have whole numbers. Whole numbers are denoted by symbol W. So whole numbers start from 0 and include all natural numbers, 1, 2, 3, and so on. We can say that every natural number is whole number, but every whole number is not natural number. Okay, then we have integers. Integers are denoted by symbol Z. So integers are in fact the whole numbers and their negative counterparts. So we have here -1, -2, -3, and so on. We have smallest natural number is 1, smallest whole number is 0, but we cannot say we have a smallest integer. Okay, so small integers are whole numbers and their negative counterparts. Then we have rational numbers. Rational numbers. Rational numbers are denoted by Q. Now here we can say all whole numbers are integers, all natural numbers are integers, but all integers cannot be whole numbers or natural numbers. Then we have rational numbers. So we say a number is said to be a rational if it can be written in the form of P upon Q, P by Q form, okay, where P and Q are integers, they belong to integers, and Q is not equal to 0. That is, denominator is not equal to 0. Let us suppose we have 2. 2 is a rational number because we can write 2 like this, 2 upon 1. It will remain 2 here, okay. So it is in the form of P by Q. Here P and Q are integers, so 2 and 1 they are 2 and 1 they are integers, and the denominator is not equal to 0. So 2 is a rational number. Likewise, if we have negative 1 upon 4, okay, this is also a rational number. Why? It is in the form of P by Q, and negative 1 and 4 they are integers, and denominator is not 0. So this is in fact a rational number. What about 0? 0 in fact is a rational number because we can write 0 in the form of 0 upon 1, so it is in the form of P by Q, and here 0 and 1, that is P and Q, they are integers, and denominator is not equal to 0. So this is also rational number, this is also rational number. But what about 5 upon 0? 5 upon 0, let us suppose it is in the form of P upon Q. Here 5 and 0 are belong to integers, but here 0, that is denominator is 0, so this cannot be a rational number here, okay. Then we have the irrational numbers, okay. So in the rational number, what we will have real. So all the integers are rational numbers, but all rational numbers are not integers, okay. So in the rational number we will have 1, 0, negative 1 upon 2, 5, 2 upon 3, okay. These are all rational numbers which can be written in the form of P upon Q, okay. Then we have irrational numbers. Irrational numbers. Irrational numbers are denoted by letter I. So numbers that are not rational are called irrational numbers. Like we have under root 2, we have pi, we have Euler's number. These are all called irrational numbers. In fact, under root 5, it is also irrational number. So these are all irrational numbers. Now we have the set of real numbers. Now what is a real number? Real numbers. Real numbers are denoted by letter R. So real numbers is a set that includes irrational numbers and rational numbers. So here we have the rational numbers, and irrational numbers. Irrational numbers. Okay. So the set of all rational and irrational numbers are called real numbers. If we show, graphically how it will look like, so let me show it here. Let us suppose we have this circle denotes the set of natural numbers, okay. Then we have whole numbers. Whole numbers contains natural numbers. Let us denote it by W, okay. Then what about integers? So integer, let us suppose this circle denotes the integers. So integers include whole numbers and natural numbers, and here we can see every whole number is integer, but every integer cannot be whole number. Likewise, every natural number is whole number, but every whole number is not natural number. Then we have, let us suppose this circle denotes the rational numbers, okay. So rational numbers include integers, whole numbers, and natural numbers. Then we have another set, what we call the irrational numbers, okay. So this is in fact disjoint from the rational numbers. Now this entire circle is called real number. So this entire circle denotes the real numbers. Okay, so we can say every irrational number is a real number, but every real number is not irrational. Okay, so this whole circle denotes the region containing rational numbers and irrational numbers. Okay, so then we have another, so this is called the real, these are called real numbers. Okay, then we have another set, let us denote it by this. This is called the complex numbers. So we don't need to discuss about the complex numbers. So to explain it, complex numbers, although its name is complex, it is not complex per se. So a complex number is a number expressed in the form of, that is z is equal to a plus iota b, where a is a real number and this is what we call this is the real part and this is the imaginary part. Okay, where this iota is the square of -1. Okay, like if I have a number 3 plus 2 iota, this is called complex number. Okay, so this is entirely different from the real number system. Now let's take the intervals as subsets of real numbers. Let us learn about this. Okay, so by intervals what we mean, intervals are subsets of real numbers that represent a continuous range of real numbers expressed using the specific symbols we use, the brackets. Okay, so first of all, the set of real numbers, graphically we can show it. The set of all real numbers is a complete unbroken number line. It includes all numbers, whether positive, negative, integers, rational numbers, irrational numbers, fractions, decimals. Okay, so let us suppose this is this denotes the real numbers. Okay, now real numbers, let us denote R as a set of all real numbers. Set of all real numbers. And let us take two numbers. Let us suppose we have two numbers a and b, such that a and b belong to real numbers. Okay, such that a is less than b. Okay, now how do we show it in the interval notation? So let us suppose x is a set of all real numbers. Okay, and x belong to a, b. We call this closed interval. Okay, when we take square brackets, we say it is a closed interval. So this is closed interval. And on the number line, how can we show it? Let us suppose we have this number line. Okay, if I show, let us suppose this is point A, this is point B on the number line. Okay, what happens here? We include both numbers a and b when we take the closed interval. That means the all real numbers between a and b, okay, including a and b. Okay, this is a closed interval. Likewise, let us suppose x belongs to ab. Okay, this what we call the open interval. So on the number line, how do we show it? Since it is an open number line, so the all numbers between a and b. Okay, so all numbers between a and b excluding a and b. So here I have not shaded these two holes to show it here. Okay, so this is called the open interval. So here we have this bracket and here we will have square bracket when we include both the numbers. Then we have, let us suppose x belongs to, and let us take this first, we have AB. This is what we call, here we have the square bracket on the left side and we have the parenthesis on the right side. We call this interval as closed open. We call it closed open, or we also call it semi-closed or semi-opened. Okay, so on the number line it will be like this. Let us suppose we have this number line and we have two numbers a. Here we include this a but exclude this b, okay, because it is closed from the left side and open from the right side here, okay. So here we will have this bracket, we will have this bracket, here we will have this closed bracket. Then likewise we have, let us suppose x belongs to, x is a number that belongs to, or open from the left and closed from the right, okay. We call this as closed open, rather open closed. So we start from this open closed, this is called a closed open interval, okay. So we call this open closed, open closed. And on the number line what we have, from the left it is open, so let us put a hole here, and from the right it is closed. Let us color this. So these are basically the types of intervals. Now how do we show it in the set form? So we can write in the interval notation. Let us suppose in the set notation we write it like this. So let us suppose S is a set, okay, that contains all elements x such that x belongs to all real numbers, and let us suppose x lies between -6, that is, it is greater than -6 but greater than less or equal to 5, okay. So how do we show it in the form of interval notation? So we can write it like this. So this is -6 comma we have 5, but since from the right side it is closed and on the left side it is open, okay. Likewise we can take other examples. Let us suppose we have a set b. B is a set of all x's such that x belongs to real numbers, and let us suppose x is less or equal to 1, greater or equal to 1 but less or equal to 2. So in the interval notation we can write it by the closed interval, that is 1 comma 2, and we use the square brackets here, okay. And likewise let's take another. Let us say we have set C, contains all x's such that x belongs to real numbers and x is less than, let us suppose, x is greater than 1 but less or equal to 4. So in the interval notation we can show it like this. So it is open from the left and closed from the right. That is shown by this sign. Likewise we can form different intervals here. Now let us learn the difference between this symbol which is belongs to and this symbol which is the subset, okay. So this symbol shows us belongs to, and it means individual element being a member of a set, and this symbol shows the subset, which means entire set is a collection of elements, all of which are also members of the larger set. And let me give you an example. So let us suppose I have a set A which consists of numbers 1, 2 and 3. I have also another set B which has the let us suppose the numbers 1 and 2. Now in this case, when I say, if I take element 1 in this, so I say individual member or individual element belongs to set A. Likewise I can say 2 belongs to A, and likewise we can say 1 belongs to B. In this case 1 belongs to B, 2 belongs to B, okay. What is the difference? Now what about this symbol? So this symbol means entire set is a collection of members, all of which are also the members of larger set. So when I say that this set B is a subset of A, what I mean this time, I am saying that this entire set 1, 2, this entire set are also members of the larger set of this set, okay. For that we use this symbol, okay. When one set, all the elements of one set, or what we can say belongs to, a larger set, we use this very symbol. Okay, so the difference lies in the relationship being described. Okay, an element to a set relationship is shown by this symbol belongs to, and a set to a set relationship is being shown by this symbol, what we call subset. And let me write it here. If I have the space, so let me make some space. So the difference is an element to a set, an element to a set relationship. It is being shown by this symbol, what we call the belongs to, because here 1 is the element and A is the set. So the relationship between element to a set is shown by this symbol. Likewise, so let me see if I have space, or let me create someone. Okay, then we have this relationship, that is a set to a set relationship. A set, okay, I have the space, a set, but I don't have the color. So a set to a set relationship, oh no, this is shown by this symbol, that is the subset. So the difference lies in the relationship being described. An element to a set relationship, or belongs to a set relationship for a subset. Okay, let us take a question on sets. Let A be a set consisting of elements 5, curly bracket 5, 1, curly bracket 1, comma 5, then we have 2. Which of the following are true? We are being given the statements and we need to find which statement is true. Okay, so let us first break down the elements of the set. So first we have, let me write it here, elements. So 5 is an element, then the set containing 5, okay, the set containing 5 is also element of A. Then 1 is an element, the set containing 1 comma 5, this is also element of A, and 2 is the element of A. So we have 1, 2, 3, 4, 5 elements here. Okay, now what is the difference between belongs to and subset? Now belongs to shows us the relationship between element to set relationship. Okay, and belongs to shows us the set to set relationship, Okay, let us suppose A is a set containing elements 1, 2, 3, B is another set containing 2 and 3. We can say here that 1 belongs to set A, so belongs to shows us element to set relation. 1 is an element of set A, so 1 belongs to set A. Likewise, can I say B is the subset of A? Yes, because all elements of B are also present in A. So here I cannot say 1 belongs to A. This would be incorrect. And why? Because 1 is not a subset here. 1 is an element. Likewise, I cannot say here B belongs to A. Why? Because B is a set. Okay, the set to set relationship is being shown by this symbol. Okay, so this will be incorrect here. Now let's come to the question. So these are the elements here. So we are being told 5 as an element belongs to A. Yes, this is true. We have an element 5 in this set. Now next, the set containing 5 belongs to A. The set, we have the set 5 the set containing 5 here. It is an element of A. Yes. Then we are being so told, or rather, the set containing 1 is an element of A or belongs to A. So there is no set like this we have as element here. So this is in fact incorrect. Now 2 comma 5 is a subset of A. Now from these we can form the subsets also. Okay, so if I take, let us suppose from elements we can form subsets 5, 2, 5 and 2. So this is the subset of A. Okay, so this is correct. 5 and 2, we are being told 2 and 5. Order does not matter here. So this is in fact true here. Now we are being told 2 belongs to A. Sorry, 2 is a subset of A. My mistake. 2 is a subset of A. Is 2 a subset of A? No. 2 is not a subset of A. Here we can say we have the elements here. 2 is in fact an element of A. So this is incorrect. If it were like this, 2 belongs to A, then it would have been true. Likewise, in this case, if we were told that 1 belongs to A, this would have been true. But the subset containing 1 is not present here. Now another one is we are being told 2 is an element here. Okay, is this element present here? No. The set containing 1 is element. No, we don't have. We have 1 as an element, not the set 1 as a set containing, sorry, not like the set containing 1 as element. So this is in fact false. We are being told there this is not a subset of A. That's true now. Okay, since we are being told whether this statement is true. So 2 and the set containing 1 is not a subset of A. This is in fact a true statement. Now let's come to this one. So we have the elements 2. Is there any element, sorry, the set containing 2 as an element? No, we have 2 as an element, not the set containing 2 as an element. Likewise, the set containing 1 as an element. No, we don't have in this case, you can see here. So we are being told that this is not a subset of A. Yes, that's also true. Now what about this 8th one? We are being told 5. Is 5 an element here? Yes, 5 is element here. Now is the set containing 5? The set containing 5, yes, this is also present. The set containing 1 and 5, the set containing 1 and 5, these are the elements. From elements we can form the subsets. So this is also element here, and we are being told this belongs to subset A. Yes, that's true now. Now we have the 9th one. The set containing 5, okay, is a subset of A. Yes, because we have this set. So the set containing 5 is a subset of A. That's also true here. Okay. Now let's take a question on power set. If A is a set which consists of 5 curly bracket 5, then the power set P of A of the given set A is, we need to find out. Okay, so we have the set A which consists of element 5 and the set containing element 5. Okay, basically we have the 2 elements here. Okay, we need to find out the power set. So what is power set? Power set is the all possible subsets of a given set. So power set of A, the number of subsets will be equal to 2 to the power the number of elements in the given set. Since we call this the cardinality of the set also, 2 to the power n, where n is the cardinality. Cardinality simply shows the number of elements. So we will have 2, since we have 2 elements here, 2 square, which is 4. In the power set we will have 4 subsets or rather. Okay, now what are the elements here? So elements are 5, then the set containing element 5. Now in power set A, the number of elements, we know we always include 5 and the set itself. These are the 2. So 5, every set contains the null set as its element. Okay, 5. Then we have this subset, that is 5, the subset containing 5. Then since we treat it as an element, this is an element, now we take its subset. So its subset will be this. Okay, we will have another subset like this. We treat it as an element since we have 2 elements, and we take its subset here. Okay, then the set itself. So what is the set itself? It is pi, comma, okay, so we have 1, 2, let us take another bracket now. That means power set A will have elements 5, this the set containing element 5, since this is an element, it is a subset. Okay, 5 and it is subset. Then this is the set itself, where A is equal to this. So we have 1, 2, 3, 4. So the number of number of subsets in a power set will be equal to 4 here. Okay, so the correct option should be A is not correct, B is not correct, C, we have 5, this and this, so we have 4 elements, so the correct option should be C option. Okay, so let me give you a quick recap of if we have a set A which consists of numbers 1, 2 and 3. Okay, then the power set of A will be the all possible subsets of this given set. So first subset will be, so let me write it here. So first subset will be 1, second will be 2, third will be 3, fourth will be 1 and 2, 1 comma 2. Likewise, we will have 1 and 3, 1 and 3. Then we will have 2 and 3, 2 and 3. And lastly, we will have the set itself. And we always include the null set, that is 5. Okay, here you can see the number of subsets is 1, 2, 3, 4, 5, 6, 7, 8. So power of set is 2 to the power the number of elements. So since we have 3 elements here, you can see here it is 2 cube, which is equal to 8 here. Now let us discuss about the union, intersection and difference of sets. We consider two sets, let us say A and B. Then A union B means the set of all elements that are in set A, in set B, or in both sets. Okay, so let's take an example. Let us suppose we have set A, which consists of elements 1 and 2, and we have B set, which consists of elements 2 and 3. Then A union B is a set, okay, the set of all elements that are in set A, which are in set B, or in both. So the union will be, so we have 1 here, we have 2 here, we have 2 here also, we will not include it, it gets repeated. So then we have 3. So this will be the A union B, the set of all elements that are present in set A, in set B, or in both the sets. So how do we show it within diagram? Let us suppose this is set A, it contains 1 and 2, 1 and 2. Then we have set B, it contains 2 and 3. Okay, so this is set A, this is set B, and it contains 3. Now what happens in union? We consider all the elements which are in set A. So this all area will be the union, which are in set B or which are present in both sets. Here you can see set A contains 1 and 2, set B contains 2 and 3. Then union will be the elements present in set A, which is 1, in this case 1 and 2, the elements present in set B, which is 2 and 3, and the elements which are both in A and B set. So we have 1, 2 and 3. Likewise, let us take example of A intersection B. Intersection is denoted by this inverted U symbol, the set of all elements that are common to the both sets A and B. Okay, now given this example, okay, if I draw it again, so what will be the intersection? The elements that are common to the both sets will be included in the intersection. So we have here 1 and 2. Okay, I'm taking the first example. This is set A, this is set B. So A intersection B means the set of all elements that are common in both sets A and B. So here you can see only 2 is common to both the sets A and B. So this area, the elements present in this area will be the set of A intersection B, and here we will have only one element, which is 2. Okay, in A union B we have 1, 2 and 3. Now we have another A minus B, that is difference of sets, the set of all elements that are in set A but not in set B. Okay, now again taking this example, that means A minus B, A minus B. So let us draw this time the two sets again. So we have, let me draw it here. So we have A contains 1 and 2. Then we have B contains 2 and 3. Now the difference of sets is, the difference A minus B is the set of all elements that are in set A but not in set B. So since A is equal to, in A we have 1 and 2, in B we have 2 and 3. Now the difference is the set of all elements that are in set A but not in set B. So A minus B will be this very region. So this region. Okay, so A minus B will consist of element of 1 only. Okay, then we have, I hope you got the idea what is meant by the union, intersection and difference of sets. So in the difference, what we see, then the numbers or the elements that are present in set A but not in set B. Okay, so since B is this very, so we subtract, we have this set, from this we subtract this area. Okay, so only one element is present here. Now we take another set, what we call the universal set. Okay, if I have the space I can show it here, or for that let me rub this out. Now what is universal set? Now we have universal set. Universal set. Now universal set is the set of all elements under consideration in a given problem. So the set of all elements under consideration in a given in a given problem. Now let me rub this out. It is denoted by U, okay, or we denote it by A, the universal set. Let us denote it by E. Let us suppose we have a set universal which consists of elements 1, 2, 3, 4, 5, 6. Okay, this is our universal set. Now on the diagram we denote the universal set by the rectangle. So this universal set, so all the elements present in this rectangle represent the universal set here. So let us denote it by E here. And let's take another set. Let us suppose we have a set A which consists of elements 3, 4 and 5. Okay, now we need to define what is meant by the complement of a set. Okay, so complement of a set. Okay, by complement what we mean, the set that includes all elements, the set that includes all elements which are not in set A but still settle in the universal set. Okay, so complement is denoted by, if I have set A superscript C, so it denotes A complement or A prime. These are the denotations or notations for A complement. Now let's come to the question. So we have this universal set here, and we have a set in the universal set which contains 3, 4 and 5. So let us denote. So we have numbers 1, let us say 2, then we have 3, 4, 5, 6. So this is the universal set. Now in this universal set we have this subset which is A. Okay, now what happens here, since we need to find out the complement, that is A complement will be equal to, so A complement will be equal to, it will be equal to the universal set minus the elements present in set A. Okay, so simple thing, the set of all elements in a given universal set that are not in set A. Since we have denoted universal set by E, that is denoted by E here also. So what happens, all the elements that are not in set A but are still in the universal set, so that will be the A complement. So A complement will be this very region excluding the set A. So the numbers or the the elements in A complement will be 1, 2 and 6. So we will have 1, 2 and 6. They will be the A complement here. Now here we can also see some of the properties of the universal set here. Okay, briefly. So the union of set A, in this case the union of set A and the universal set gives us the universal set. Okay, so here you can see set A contains 3, 4, 5. Now union with the universal set, so universal set contains 1, 2, 3, 4, 5, 6. So the union will give us the universal set, that is the set of all elements which are present in set A, set E, which is universal set, or in both. So here it will be equal to 1, 2, 3, 4, 5, 6. So again we get the universal set. So this is A union universal set. It gives us the universal set in return. Okay. Now another property of the universal set is that, or let me rub this out. The intersection of set A with the universal set gives us A. So A intersection, the universal set will give us A. So how do we show it? Since we know that in A we have 3, 4, 5 intersection. In universal set 1, 2, 3, 4, 5, 6. Now the common element is, of A and E denotes our intersection. So here you can see A intersection E will be equal to, so the common elements are 3, 4, 5. Here we have 3, 4, 5, 3, 4, 5, and A intersection E will be equal to, so 3, 4, 5 is our A. Okay. So on the diagram, if I show it on the diagram, okay, let me take small diagram this time. So we have 1, 2, 3, 4, 5, 6. This time this is set A. Okay, this is set A and this is the universal set. Now this time A intersection universal set will be this region. Okay, so this A intersection is equal to A. Now let's take the question on the operations on sets. Let E be the universal set which contains numbers from 1 to 9. Then we have set A which contains numbers from 1 to 4. Then B contains 2, 4, 6, 8. C is another set which contains 3, 4, 5, 6. We need to find out these things. So let's take it one by one. So first we need to find out the A complement. Okay, so A complement will be equal to, so let me draw here the universal set first. So in the universal set we will have all the elements. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so this is our universal set. In the universal set we need to find out the A complement. So first we need to find out the set A. So set A contains 1, 2, 3, 4. So 1, 2, 3, 4. Let us encircle this. So this is our A set. Okay, now the A complement means the set which contains all elements in the universal set except the elements that are present in set A. So it is equal to the universal set minus the elements present in set A. So when we subtract, we will be left with these elements. So in the A complement we will have 5, 6, 7, 8, 9. Pretty simple. Okay. Now we need to find out the B complement. B complement, and for that let me draw the universal set again. Okay. So let us draw here. So let us say this is our universal set. We have 2, 4, 6, 8. So let me write it here. 2, 4, 6, 8. In the universal set we have 1, 2, 3, 4, 5, 6 is here, 7, 8 and 9. Okay, so B complement will be, now let us first find what is B. B is this very set. Okay, so it will be equal to the universal set minus the element is present in set B. So in this case, this region, the element is present outside the set B will denote the complement of set B. So we will have 1, 3, 5, 7, 9. 1, 3, 5, 7, 9. Okay. Now third one is to find out A intersection C complement. So A intersection C complement. Okay, so first we need to find out the A intersection C. Okay, so A intersection C will be, and let us draw the universal set again to explain it. So first we need to find out A intersection C. So in A we have 1, 2, 3, 4. Here we have 3, 4, 5, 6. Okay, so we have in A we have 1, 2, 3, 4, and in C we have 3, 4, 5, 6. Okay, now the A intersection C are the elements that are present in both the sets. So A intersection C will be equal to, so we have 2 3 4, here we have 3 4, so 3 and 4 are present here, so you will have 3 and 4. Okay, so if I show it here, let us say this is A contains 1 2 3 4, so we have 1 2 3 4. Then we have C, let us suppose this is A, this is C, so in the C we have 3 4 5 6, so we have 3 4, then we have 5 6. Okay, then we are left with, since this is the universal set, so we have 1 2 3 4 5 6, we have 7 8 9 here. Okay, we calculated A intersection C as 3 and 4, then A intersection C complement will be equal to A intersection C will be the elements that are present outside A intersection C. Okay, so these vary the numbers or the elements which are outside A intersection C, which will be equal to the universal set, okay, minus A intersection C. So A intersection C. Now in A intersection C we have only these elements, okay, 3 and 4, and outside A intersection C we will have all the elements, and here you can see, and that is denoted by E, not to confuse them with the union. Okay, so when we subtract A intersection C, since A intersection C is only 3 and 4 from the universal set, we will get A intersection C complement, and here you can see the A intersection C will be equal to, so we are left with 1 2 5 6 7 1 2 5 6 7 8 9 1 2 5 6 7 8 9 7 8 9. Okay, now we need to find out A union B complement. So for that, let me again rub this. We have, first we need to find out A union B. Okay, so first we need to find out A union B. So for that, let me draw the universal set first. So this is our universal set. Now A union B will mean the elements which are present in set A and set B are in both. So here A is equal to 1 2 3 4. In B we have 2 4 6 and 8. Now in A union B we will have 1 is here, then we have 2, then we have 3, 4 is repeated, then we have 6, then 8. Okay, now let us draw this on the Venn diagram also. So here we have 1, then we have 2, then we have 3, then we have 4, then we have 6 in set A. What about set B? In set we have 2 and 4, so they are overlapping here. So we have 2 4, then we have 6 and 8. Okay, this is set B. Now A union B is this whole area, but what are the elements in the universal set? Let us see. So we have 1 2 3 4 5 is not here, 5 1 2 3 4, so we have 1 2 3, so 6 is not here, so we have 5, so we have 1 2 3 4 5 6 7 8 and 9. Okay, so since universal set is from 1 to 9, this is our A union B, then A union B intersection will be equal to the universal set minus A union B. When we subtract A union B from universal set, we get A union B complement, and here you can see we will have 5 7 and 9, 5 7 and 9. Okay, next we have the complement of A complement, the complement of A complement. Okay, we have calculated A complement is this, so A complement will be equal to universal set minus the complement of A. And let us find out what will be there. Now, when we subtract the complement of A from universal set, we will get, let us see what we will get. So in the universal set, we have these numbers. Complement of A is 5, 6, 7, 8, 9. 5, 6, 7, 8, 9. So we will be left with 1, 2, 3, 4. And 1, 2, 3, 4 is the set itself. So the complement of A will be equal to A itself. Okay. Now let's take B minus C complement. Okay. So we have B minus C complement. It will be equal to universal set minus B minus C. Okay. So first we need to find out B minus C, the difference of sets. So let's take the universal set again. So we have universal set E, and let us see what are the elements here. So in the B we have 2, 4, 6, 8. 2, 4, 6, 8. In C we have 3, 4, 5, 6. Okay, 6 is here and 8 also here. So let us take, we have 2, 4, 6, 8 in B. In C we have 3, 4, 5, 6. So we have 3, 4, 5, 6. Okay. Now what is B minus C? When we subtract the elements, when we subtract the elements that are in C from B, we get B minus C. So this very region will denote B minus C. Okay, so it will be here B minus C will be equal to 2 and 8. Now when we subtract 2 and 8 from the universal set, okay, we will be left with, so in the universal set we have 1, 2 is here, 3, 4, 5, 6, 7 is not present, then we have 9. Okay, so when we subtract this region from the whole universe, we will get B minus C complement. So it will be equal to, so we will have 1, then we have 3, 5, rather we have also 4 here, so we have 4, 5, 6, 7 and 9. So this will be B minus C complement here. Let us take another question on sets. Let A is a set of all x such that x belongs to natural numbers. We have another set B is a set of all x such that x is equal to 2y and y belongs to natural numbers. Then we have set C is the set of all x where x is equal to 2y minus 1 where y belongs to natural numbers. And we have set D which contains the prime natural numbers. We need to find out A intersection B, A intersection C and A intersection D. Okay, so let's write these sets in what we call in the roster form. So we have set A. So what will be the elements in set A? Since we are being told that x, set A is the set of all x such that x belongs to natural numbers. So we know that it will be 1, 2, 3, 4, 5, 6, 7 and so on. This is the first set. Now set B, the condition is that it contains all x such that x is equal to 2y where y is equal to natural number. So natural numbers start from 1. So when y is equal to 1, when y is equal to 1, so x will be equal to 2 into 1 which is equal to 2. So first element will be 2. Then when y is equal to 2, when y is equal to 2, okay, then we will have 2 into 2 which is 4. So here we will get 4. So second element will be 4. Likewise, when y is equal to 3, so x will be equal to 2 into 3 which is equal to 6. So we will get the odd numbers here, even numbers. Then we will have 8, 10, 12, 14 and so on. Okay. Then we have set C. Set C, it is equal to, it comprises of all x such that x is equal to 2y minus 1 where y belongs to n. So let us break this out also. So when y is equal to 1, x will be equal to 2 into y is 1, 2 into y minus 1, we will get 1. Okay. Likewise, when y is equal to 2, we will get 2 into 2 is 4 minus 1 which is 3. So next element will be 3. Likewise, when y is equal to 3 here, so we will have 2 into 3, 2 3s are 6 minus 1 which is 5. So we will get all odd numbers here, 5, 7, 9, 11, 13, and so on. Now what about D set? So in D we will have, so we are being told x is a prime natural number. So in D we will have, so first natural number comes out to be, sorry, first prime natural number is 2, then we have 3, then we will have 5, then we will have 7. So we have prime natural numbers here. Then we will have, since we talk about the natural prime numbers, then we will have 11, 13, then we have 17, I guess, and so on. Okay, now we are being told to find out A intersection B. Now we need to find out A intersection B. Okay, so A intersection B means all the common elements of A and B. Since A contains 1, 2, 3, 4, 5, 6, 7, and B contains 2, 4, 6, 8, 10, 12, 14, that means A intersection B will be equal to. So if I draw it on the Venn diagram, or if I show it by sets, let us try to see here. So we have, it contains 1, how do I put it here? So let me see. A intersections B means the common elements. So common elements will be obviously, since in A we have 1, 2, 3, 4, 5, 6, 7, 8, 9. In B we have 2, 4, 6, 10, 12, 14. So we will have like this: 2, 4, 6, 8. Here we have 1, 2, 3, 4, 5, 6, 7, 8, and so on. Okay. In set B we have 2, 4, 6, 8. So set B will be in this region. So the common region between A intersection B, it will be obviously equal to set B. It will be equal to set B here. Okay, I hope I am making sense here. Now A intersection C. Now let us see. In A we have all the natural numbers. In C we have the odd numbers. Okay, the intersection of these will be in fact this set C. Okay, again let us take the example of two sets. Okay, in set we have, let me write it here, 1, 3, 5, 7, 9. Okay, let us suppose in set A we have 1, 2, 3, 4. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 up to infinity here. Okay, so in set C we have 1, 3, 5, 7, 9, 13. So here you can see, since this is set A, in set C, so A intersection C will be in fact equal to this set C. So A intersection C is equal to C here. Now let's take the last one, A intersection D. Again, in D we have prime natural numbers. In A we have all the natural numbers. So it will look like this. So let us take first this 2, 3, 5, 7, 11. So we have 2, 3, 5, 7, 11, 13. Okay, but in set A we have 1, 2 is there, 3, 4, 5, then 6, 7 is here, 8, 9, 10. Okay, let us suppose this is set A and we have infinite number of elements here. Now in set D we have only 2, 3, 5, 7, 11. Again you can see this region denotes our D, and the common region is in fact that set D itself. So A intersection D in this case will be equal to D. Let's take another question on the sets. If A is the proper subset of B, then find A intersection B, A union B, and A minus B. Okay, so let us understand it with an example. Let us say A is a set containing elements 1 and 2. Then B is another set which contains elements, let us suppose 1, 2, 3, and 4. Okay, now we say that A is the proper subset of B if all elements of A are also present in B, but there are some elements in B which are not present in A. Okay, first we need to find out the A intersection B. Okay, so let us draw. Let us suppose this is set A. In set A we have 1 and 2, 1, 2. In set B we have 1, 2, 3, 4. So in set B we have 1 2 3 4. Now intersection is the set of all elements which are common to both sets. Okay, so here you can see this region is common to both elements, but this set comprises of all elements 1 and 2. So here we will get 1 comma 2, which is in fact equal to the given set A. That means A intersection B will be equal to A. Okay, now let's take the case of union. Again we have same two sets. Now A union B means the set of all elements which are either in set A or in set B or in both. Okay, so in set A we have 1 2, in set B we have 1 2 3 4. So this is set B, we have 1 2 3 4. Now this whole region will be our A union B here. Okay, the elements which are in set A and in set B or in both set A and B, and here you can see it will be equal to A union B will be equal to 1 2 3 4, but we know that 1 2 3 4 belongs to B, which is equal to B. That means A union B will be equal to B. Now we have A minus B. Okay, now we have A minus B, it will be equal to, so we need to find out the elements that are only present in A, and we subtract the elements which are present in B. So this region, here you can see in this region there is no element, so A minus B will be equal to the empty set. Here we will have only void result, so it is equal to 5. Now let us understand De Morgan's law using Venn diagram. De Morgan's law states that if we have two sets, then A and B, then A union B whole complement is equal to A complement intersection B complement. Okay, so let's take the left hand side and let us draw it as Venn diagram. So first let us draw the universal set. Okay, so let us say it is E. In this we have two sets, A and B. Let us suppose this is A, then we have another set B. Okay, this is A, this is B. Now first this signifies A union B. By A union B we mean the set of all elements which are in set A, in set B or in both the sets. So we color this entire thing here. So this shows us A union B. Okay, now we need to take the complement of A union B. So let us again draw the same. So we have the same thing. We have set A, we have set A, and we have set B. Okay, this is set B, and this is set A. Now A union B complement means the region which is outside A union B. That is, when we subtract A union B from the universal set, we get the region. So graphically the region will be this region. Okay, so let me try to do it perfectly. Okay, so this was A union B, this is A union B complement. Okay, this region, the black region. Now on the right hand side, let us take again, on the right side here we have first A complement. So let us again take the Venn diagram. We have two sets again, these sets, so let us draw them here. So we have set A and we have set B. Now here this means this is, since we need to find out the A complement here, so let me write it is here A. Okay, so A complement means this region. So how do I show it here? When we subtract set A from the universal set, we get A complement. We know this very thing. So this will be our A complement. Likewise, we need to find out the B complement. Again, let us take the same set. So we have A, then we have B. Okay, this is B, this is A. This time B complement will be the universe set. Okay, when we subtract B from the universal set, we will get the B complement. So in this case, our B complement will be this region. Now, what will be A intersection, A complement intersection B complement? And let us draw it here. So, understand it properly. So, this is our A complement. Okay. Then we have B complement. When we combine these figures, so what will we get? So, this thing and this thing. So, we will get this whole region. You can visualize it by yourself. So this will be the intersecting part. So this is here A complement intersection B complement. That means A union B whole complement is equal to, so these two diagrams are same here. So that means A union B whole complement is equal to A complement intersection B complement. Now let's understand De Morgan's law using Venn diagram. This is the second case now. De Morgan's law states that if we have two sets A and B, then A intersection B whole complement is equal to A complement union B complement. Okay, so let us take this side first. Now what is A intersection B? A intersection B means all the elements which are common to the both sets. So this red shaped region denotes A intersection B. Okay, but we need to find out A intersection B complement. Okay, so the area, this area, okay, when we subtract this area from the universal set, we will get the A intersection B complement. Okay, so this we will get the area which is shown by this red region, except for this Lennis shaped region. It will denote A intersection B complement here. Okay, this is A intersection B. I hope you are getting the point. Now on the right side we have A complement. So we have set A and set B. Now what is A complement? This denotes A complement, area which is outside this set A denotes the A complement. So this red shaped region is A complement. Likewise, we have B complement. B complement will be the area which is outside this B circle, the set B, the area outside the set B will denote B complement here. Okay, now when we combine these two here, so if I combine them, what will we get? Let us try to see. So when we combine these two, since this is our universal set, so here we have this circle. Okay, this is our A complement, this is our B complement. So we will get, let me show it here. So if you can see, this is A, then we have B, this is A, this is B here. So the area outside A, the area outside A, this is A complement. Okay, then the area which is outside B. So let us share this also outside B. So this, so you can see we got the same result. There is A intersection B whole complement is equal to A complement union B complement. Now let's understand the number of elements in sets using the properties. If A, B and C are finite sets and epsilon B universal finite set, then these properties hold. Okay, so let us take the first property. It says the number of elements in A union B is equal to number of elements in A plus number of elements in B minus number of elements in A intersection B. Okay, so let us see here what is meant by this. Let me draw a simple Venn diagram here. So this is our universal set. So we have two sets here. Let me try to draw it here. So let us we have set A, then we have set B. Now what is meant by A union B? The elements which are either in set A or in set B or in both set A and B. Okay, so this will be equal to, so this region, this whole region, it will be equal to the number of elements present in set A. So let us draw it here. Again we have the same, let us say this is set A, then we have set B. So the number of elements present in set A, so this region, plus again we take these two sets, we set A, then we have set B. So this is B, this is A, which is equal to number of elements present in set B. So we have this region. Okay, from this we subtract the region which is common here. Here we have this common region, so we need to subtract this. So again let's draw two sets here. Okay, this is A, this is B, and we need to subtract this region. Okay, then this will give us, when we add these two and subtract this lens shaped region, we will get this result, that is the number of elements in A union B will be equal to the number of elements present in set A plus the number of elements present in set B minus the number of elements which are common to both A and B, that is A intersection B. Okay, now this is the first result. Now second result tells us that if number of elements in A union B is equal to number of elements in A plus number of elements in B, then A and B are disjoint non-void sets. Disjoint means they have no element in common. Non-void means they have elements in them. Okay, so we can show this result also here. It is very simple. So let me draw the Venn diagram. For that matter, let me wrap this diagram to show the second result. So this is set A, this is set B, this is our universal set. So in this case we have the number of elements in set A union B. It will be equal to the number of elements present in, so we need to find out this very thing. So it will be equal to the number of elements present in set A, number of elements present in set A, plus we again draw these two sets A, B, plus the number of elements in set B. Now let's understand the number of elements in sets using the properties. If A, B and C are finite sets, that means the number of elements are countable, and epsilon denotes the universal finite set, that means universal set is also finite, then the first property is number of elements in A union B is equal to number of elements in set A plus number of elements in set B minus number of elements which are in both set A and B, which are common. Okay, so how do we see, or how do we understand it using Venn diagram? Let us try to find out. So let us suppose this rectangle, it is our universal set. So we have here set A and then we have set B. Okay, so the area, so the A union B is the set of all elements which are present in set A, set B, and in both set A and B. So this denotes A union B. Okay, so A union B. it will be equal to, again let us draw the same Venn diagram. It will be equal to, so we have set A, set B. It will be equal to the number of elements in set A. Okay, so it will be this very region. So let us shade this region. Okay, plus again we have two sets, A, B. This is A, this is B. It will be equal to number of elements in set B. Obviously this time we shade this very region. Okay, from there we subtract the common area. Okay, because here you can see in set A we have this very region, in set B we have again this region, so we subtract, and let me try to draw it here. So we have set A, set B, this is set A and set B. Okay, and we subtract this very region from this, then we will get the number of elements A intersection B. Okay, so we can now see number of elements in A union B. So this very shaded region will be equal to the number of elements in set A minus, sorry, plus the number of elements in set B minus the common region between A and B, that is A intersection B. Okay, this is the first one. Now let us learn about the second property, that is the number of elements in A union B is equal to number of elements in A plus number of elements in B, which double implies that A and B are disjoint non-wide sets. Disjoint means they have no element in common. So let us try to break this out. Let us suppose this is our universal set. We have two sets, A and we have B. Now union of A and B will be, so union of A and B will be, so this very region. So it is very pretty simple to see what our result will be. So it will be equal to number of, that is elements present in set A, so it will be equal to NA plus we set A, set B plus the number of elements present in set B. So this is straightforward. When this happens, we say the sets are disjoint. They have no element in common. Earlier we had, some region common between two sets. This very region, intersecting region. Since there is no, common region, so we can say they are disjoint, means they have no element in common, and non-wide, they have elements in them. Okay, so this is the second property. Now coming to third property. So number of elements in A minus B, and let me try to draw it here again. So we have two sets. Let us suppose this is set A, then set B. This is our universal set. Number of elements in A minus B. Okay, so let us suppose this is A, this is B. So from A, when we subtract B, we will get that very region, the region. So this region, do you notice? This is the region of A minus B. So this is the region of A minus B. It will be equal to, let us see here, it will be equal to number of elements in B, the number of elements in A. Again let us draw it. So we have A, B. It will be equal to the number of elements in A. Okay, so number of elements in A minus, let us draw again, this is A, this is B, number of elements which are common to A and B, there is A intersection B. So A intersection B is this very region. Again you can see when we A minus B will be equal to number of elements in set A minus the number of elements which are common to A and B. Okay, likewise if I take shaded region this time in this white region in consideration, so you can find out this B minus A by same logic. I will not show it here, so it is very simple also. So we have set A, set B, this time we have B minus A we have to do. So this very region will denote B minus A and it will be equal to number of elements in B minus the common region, that is if we have A intersection B, so this region, when we subtract this lens-shaped region from this, we will get this, the number of elements in B minus A. Now we will also take some numerical examples or word problems on this. Now let us take a word problem on the number of elements in sets. The question is, in a class of 40 students, 25 know English, 20 know French and English, and each student knows at least one language. We need to find out the number of students who know only English and only French. Okay, so let us draw the Venn diagram here. Okay, we have two sets here. The set of students who know English, that is being told they are 25. Okay, then we have the set of students who know French. We need to find out that very result. We are being told that the number of students who know both French and English, it is 20. So this region is 20. Okay, we are also being told at least one student knows one language. Okay, rather each student knows at least one language. So we know that the total number of students is 40. That means the number of students will be the union of the students who know English and French. This region, this whole region. Okay, this region, and this region, it will be equal to number of students who know English plus this circle, huh? Then number of students who know French, this very circle. From this we subtract the common region, which is number of the students who know both English and French. Now number of students who know English, that is being given us 25. Number of students who know French, we need to find out. Number of students who know both English and French, it is 20. And total number of students is 40. Now let us solve it for number of students who know French. It will be equal to, so 25 minus 20 is 5. Transpose it here, it gets subtracted. So 40 minus 5 is 35. So the number of students who know French is 35. But we need to find out the number of students who know only French. Okay, that will be equal to number of students who know only French. That will be equal to F minus E. That will be equal to the number of students who know French minus the number of students who know English. So it will be equal to the number of students who know French minus the number of students who know both English and French or English and French. Okay, so this shows us the number of students who only know French. It will be equal to number of students who know French. So simple thing, we need to find out this region. Okay, this region shows the number of students who only know French. So it will be equal to this whole circle, that is number of students who know French, which is 35, minus the number of students who know both English and French, so which is 25, sorry, which is here 20. So it will be equal to 15. So 15 will be the number of students who only know French. Likewise, to find out the number of students who only know English, it will be equal to E minus F. So it will be equal to the number of students who know English, that is being given us, minus the number of students who know both English and French. Now number of students who know English, that is being given us, that is 25. So it will be equal to 25 minus the number of students who know both the languages, which is 20. So it will be equal to 5. Okay, so the number of students who only know English will be 5. The number of students who only know French, it will be 15 here. Let's take another question on the number of sets. The question is, if A and B are two sets such that number of elements in set A is 17, number of elements in set B is 23, number of elements with A union B, which is equal to 38, we need to find out the number of elements in set A intersection B first. Okay, so let us take it one by one. So we know the property that the number of elements in A union B, it will be equal to the number of elements in A plus number of elements in B minus the number of elements which are in A intersection B. Okay, number of elements in A union B, that is being given us, is 38. Number of elements in A, that is 17, plus number of elements in B is 23, minus number of elements in A intersection B. So transpose this here, so we'll get number of elements in A intersection B will be equal to, let us add them, 7 plus 3 is 10, 2 plus 1 is 3, and we get here 40, and transpose this here, it gets subtracted. So the number of elements in A intersection B, it will be equal to 2 here. Okay, so this is to say, it is like this: total number of elements are 38. Okay, we have two sets, set A and set B. We are being told that total number of elements A union B, it is 38, and number of elements in set A, which is 17, number of elements in set B, which is 23, and the whole of this, that is total number of elements in A and B, it is equal to 38. Now we need to find out this very region. It came out to be, since this region denotes the number of elements which are both in A and B, it came out to be 2 here. Okay, now let's take the second one. Second one tells us to find out the number of elements which are only in set A. So number of elements which are only in set A, it will be equal to the number of elements which are in set A minus the number of elements which are present in both set A and B. Okay, this shows the number of elements which are only in A. Okay, so it will be equal to number of elements in A, that is being given us as 17, minus the number of elements which are common, which is 2. So it will be equal to 15. So if I draw it on the Venn diagram, so this is A, B, A minus B means this very region. Okay, so this denotes A minus B, number of elements in A minus B, that is the number of elements which are only in present in set A. Okay, it is equal to the number of elements which are present in set A minus the number of elements which are, so this whole circle, from this we subtract the common circle, that is the intersecting circle, A intersection B. That will give us the number of elements which are in only A, this region. So it came out to be 15. Likewise, to find out the number of elements in B minus A that are only in set B, it will be equal to number of elements in set B minus the number of elements which are in both A and B. So it will be equal to number of elements in B, that is being given us as 23, minus the number of elements which are in A intersection B, which is common, which we got here is 2. So the number of elements which are only in set B will be equal to 21. So it will look like this. So this A, this is B. This time we are being told that to find out the number of elements which are present in this region. Okay, it will be equal to this whole circle minus the common circle, sorry, the common region. So common region is the intersecting region, and number of elements in B is 23, and number of elements which are in both A and B, which is 2, which gives us 21. Now third one tells us to find out the number of elements in exactly one of A and B. Now what is meant by this? We need to find out the number of elements in exactly one of A and B. That means A triangle B. So what does A triangle B show us? It shows us the number of elements who are only in set A, or let me try to show it here to explain it. So let us suppose this is set A, this is set B. Number of elements in exactly one of A and B means the number of elements which are only in set A, sorry, in this region, okay, only in set A, plus the number of elements which are only in set B. Okay, this gives us A triangle B. So it will be equal to number of elements which are only in set A, it is equal to A minus B plus number of elements in set B only, which is B minus A. We calculated this, it is 15, which are only in this region, plus which is in this region we calculated as 21, so it will come out to be 36. Now next question is, let A and B be two sets such that the number of elements in A is 35, number of elements in A intersection B is 11, and the number of elements in A union B complement is 17, and the number of elements in universal set is 57. We need to find out the number of elements in B, number of elements which are only in A. A minus B means only those elements which are present in A, and number of elements in B minus A means the number of elements which are only in set B. Okay, so let us try to draw the Venn diagram here first. So we have the universal set. This time we are being told that in this rectangle we have 57 elements. Okay, also we are being told, let us suppose this is set A, this is set A, and this is set B. Okay, let us see what is the information given. We are being told that the number of elements in set A is 35. So this whole circle, the number of elements are there 35. Also the number of elements in A intersection B. So this is 11, A intersection B, which is common to both of the sets. We have to find out the number of elements in set B. Okay, so this whole circle we need to find out. So how do we find out it? We are being told that number of elements in A union B intersection, A union B complement is 70. So by this statement what we mean? So if I draw another Venn diagram to explain it to you. So what is A union B? So let us say this is A, this is set B. So this region denotes, this whole region denotes, this region denotes A union B. But what about A union B complement? So when we subtract this region A union B region from the universal set, we will get this region. Okay, so this region, this black region. Are you getting my point? We are being told that this black region is 17. Okay, we need to find out A union B first. Okay, what will be equal, what will be the area of this blue shaded region? The area of, rather the number of elements presented in this blue shaded region, it will be equal to, so number of elements in A union B, or let us first find out like this. So the number of elements which are outside this blue region, this is denoted by A union B whole complement. So this region denotes the number of elements A union B whole complement. Okay, it will be equal to the universal number of elements in the universal set minus this very region, number of elements which are in A union B. Okay, so this region is our A union B. So we are being told it is 17 here, this outside region is 17, which will be equal to number of elements in universal set that is being given us is 57 minus the number of elements present in A union B. We need to find out this very thing. Now solving this, so number of elements in A union B will be equal to, it will be equal to 57 minus 17. So number of elements in A union B, it will be equal to 40 here. Okay, so the area of this very region is 40. Since we got A union B, we can solve all other things now. So number of elements in A union B, we calculated as 40. Now we can use the formula, that is, so this region is A union B. So we know that the number of elements in A union B, it will be equal to number of elements in A plus number of elements in B minus the number of elements which are both in A and B. So A union B is 40. Number of elements in A, we are supposed to find out, rather that is being given to us, which is 35. Number of elements which are in B we need to find out, and A intersection B, it is being given us is 11. So it will be 40, 35 minus 11. So it will be 5 minus 1, which is 4, 3 minus 1 is 2, plus number of elements in B. So number of elements in B will be equal to 40 minus 24, which will be 16, I guess. So the number of elements in B will be 16. Now we need to find out the number of elements in A minus B, that is the number of elements which are only in A, that is meant by A minus B. It will be equal to the number of elements which are in A minus the number of elements which are in both A and B. So number of elements in A is being given as 35, so it is 35 minus common is 11, so it will be 24. Likewise, so this region denotes number of elements which are only in A. Now we need to find out number of elements which are only in B. Number of elements which are only in B, that means B minus A, it will be equal to number of elements which are in B minus the number of elements which are in both A and B, A intersection B, that is this very region. So it will be equal to number of elements in B is 16 minus the number of elements in this is 11, so it will be 16 minus 11, it will be 5. Okay, that are only in this region, and which are only this region we calculate is 24. Let us take another question on sets. The question is, if A and B are two sets such that epsilon denotes the universal set, such that the number of elements in universal set is 700, number of elements in set A is 200, number of elements in set B is 300, and number of elements in set A intersection B is 100. We need to find out the number of elements in A complement intersection B complement. Okay, so whenever we have this kind of stuff, okay, we apply the De Morgan's formula that tells us that A complement intersection B complement is equal to A union B whole complement. We know it from the De Morgan's law, and we have explained it earlier. Now what we are being given? We are being given the relations. So first let us find out A union B. What will be A union B? We know that number of elements in A union B, it will be equal to number of elements in A plus the number of elements in B minus the number of elements in A intersection B. Okay, so number of elements in A union B will be equal to number of elements in A, that is being given as is 200, plus number of elements in B is 300 minus the number of elements in A intersection B, it is 100. So number of elements in A union B will be equal to, so we have 2 plus 3 is 5 minus 1, which is 400. But we are supposed to find out this thing. So what will we do here? So we need to find out this thing. So the number of elements in A union B whole complement, it will be equal to the number of elements in universal set minus the number of elements in A union B. So the number of elements in A union B whole complement will be equal to number of elements in universal set is 700 minus number of elements which is in A union B, which is 400. So we got it A union B whole complement is equal to 300, which is in fact equal to the number of elements in A complement intersection B complement. Okay, because we know this property here. Now let's understand about law of the algebra of sets. So first we have the union of set A with itself gives us the same set. Okay, it is pretty obvious. When we take union of a set with itself, it will give us the set itself. We call this idempotent law. Idempotent law. Okay, next we have A intersection the universal set. It gives us the set A. Okay, if I have, this is our universal set and there we have set A. Now the common region between universal set and set A is in fact the set A itself. Okay. Then we have a union pi. Okay, the union of set A with empty set, it gives us A again. Okay, this is called the identity property. Then we have the commutative property, that is A union B is equal to B union A. We know this, if we have 2 plus 3, it is equal to 3 plus 2. Okay, so this is in fact union. If we replace it by plus, so it is same thing. Likewise, A intersection B is equal to B intersection A. Okay, then we have other properties, that is A union B union C is equal to A union B union C. Okay, like we do 2 plus 3 plus 4 is equal to 2 plus 3 plus 4. Okay, same properties apply here. Then we have A intersection B intersection C is equal to A intersection B intersection C. Okay, like we do 2 into 3 into 4, which is equal to 2 into 3 into 4. Okay, these are called the associative properties. We don't need to go deep into these factors. These are obvious and you can see it using Venn diagram also. Then we have the distributive property, that is A union B intersection C. This is important. It is equal to A union B intersection A union C. Okay, we know this. If we have 2 into 3 plus 4, how do we do this? So we have 2 into 3, 2 into 3 plus 2 into 4. Okay, so A union B intersection C is A union B, then we have intersection A union C. Okay, likewise we have A intersection B union C, it will be equal to A intersection B union A intersection C. Then we have the De Morgan's law. We know that is A union B, and I have explained it earlier. Whole complement, it is equal to A complement intersection B complement. We call this De Morgan's law. Likewise, if we have A intersection B whole complement, it is equal to A complement union B complement. These two are called, these are important results. We call them De Morgan's law. Now let us take another question. The question is A intersection B complement is equal to, options are being given. We need to find out the correct option. This is an important result. Okay, so we have set A. Okay, then we have set B here. We have two sets here. Now this red shaded region denotes set A here. Okay, now let us draw another Venn diagram for B complement. So let me draw it here. We have again these two sets, A and B. This is B, this is A. let us see what will be B complement. B complement, this circle B, the area outside this B circle will be the B complement. Okay, so this area, this whole area will be the B complement. Now A intersection B complement will be equal to, let us visualize what will be the resulting answer. So again we have two sets. This is set A and set B. The intersection area will be, if you visualize this red region intersection area, it will be in fact this very region. Okay, so this very region, it will be the result here. So it is equal to set A, okay, set A minus set B. That implies A intersection B complement is equal to A minus B. Only the elements which are in, that is the elements which are only in set A. Okay, so A intersection B complement is equal to A minus B. Okay, so the correct option should be A option here. Now let us briefly explain some of the important results in sets. So first we have set A minus set B, it is equal to A intersection B complement. These are important results. Next we have A minus A intersection C, it is equal to A minus is replaced by intersection, then we have A intersection C whole complement. Okay, another we have A minus A union B, it is equal to A, we replace minus with union intersection, then we have A union B whole complement. Okay, we can understand or explain all these things using the Venn diagram. If I take the first case here, so for these you can draw the Venn diagrams by yourself. Okay, so let us take A intersection B complement. So let us say we have one set, or let me take the results like this. I am explaining the first result here again. So here we have two sets, set A, set B, set A, set B, set A and set B. Okay, so we have A, B, A, B, A, B here. Okay, so let us take origins. Here we have set A. Okay, so set A will denote this region. Then we have B complement. So B is this very region. B complement will be the region outside the B circle. Okay, so it will be like this. If I show it, or let me show it with the green color. Okay, so this is our B complement. Now A intersection B complement, A intersection B complement will be equal to, let us see the common region in this set and here in B complement. If we visualize, we can see the common region will be this very part, this very part. Okay, so it is equal to A minus B. That means A intersection B complement is equal to A minus B. For other, these are the important results. Okay, you can draw the Venn diagram by yourself. Let us take another problem. Prove that for any two sets A and B, A minus B union B is equal to A union B. Okay, so we know this result. A minus B, it is in fact equal to, we have A minus is replaced by intersection and B is replaced by B complement. Okay, I have explained it earlier. Now using this, so we have LHS will be A union B complement. Okay, in place of A minus B, then we have union B here. Now let's use distributive property. We will get A union B sorry, then I have intersection, then we have B complement union B. Okay, so we have A union B intersection. Now the complement of a set with itself gives us the universal set. Let me explain it here. Let us suppose B is this very set. Okay, and let us suppose B complement is this set, the outside region of this circle B. Now B, so we have this B union B, it is in fact equal to the universal set. It will be equal to the universal set. Then we have this set intersection with universal set. Okay, so if I have A intersection universal set, since universal set is bigger than this A, so we will get the result as this A. Okay, here the result will be A union B. Why? The intersection of smaller set with bigger set is equal to the smaller set. So smaller set is here A union B. Likewise, the union of smaller set with bigger set gives us the result as bigger set. Let me write it here. Union of smaller set with bigger set is equal to bigger set. Okay, this is to, if I show it out like this, let us suppose this is set A and this is set B. Okay, now union means A union B. Since A is bigger set, B is smaller set, union will be always equal to the bigger set, which is A. Likewise here, A union B, or the intersection of bigger set with smaller set is equal to smaller set. Okay, so since smaller set is here B, that means A intersection B will be equal to B. Okay, A union B will be A. That is what I have written here. Since A union B is smaller set than the universal set, the intersection of smaller set with bigger set gives a smaller set, which is A union B, which is equal to RHS. Let A and B be two sets. Prove that A minus B intersection B is equal to 5. Let us take the LHS. So LHS we have A minus B. So we have first A. Now this minus is replaced by intersection symbol and B is replaced by B complement. I will be explaining it. Then intersection B. This is our LHS. So how do I arrive at this very result? We know that A minus B is equal to, this is the property, it is equal to A minus is replaced by intersection and B by B complement. Now we can show it on graph also. Let us suppose we have set A, set B, this is set A, this is set B. Now what is A minus B? A minus B is the elements which are only in A. So this is our A minus B. So this is our A minus B. Now why this is equal to A intersection B complement? Here you can see. So let me take another. This set A, this set B. So we have A, B. So first we have A, or let me try to draw it again. This is A, this is B. So we have A, that means this very set, it is intersected with B complement. Since this is B, this set is B, the B complement will be the area outside this circle. So the area outside this circle will be this very circle. So this is here A intersection B complement, and it is in fact equal to this circle. Okay, so A minus B, I have explained it earlier also. Having said that, let me rub this out now. So use distributive property. So we have A intersection B, then we have intersection B complement intersection B, which is equal to, we have A intersection B, intersection, we have B complement intersection B. So what does this mean? So if this set denotes B, okay, outside denotes B complement the area outside B. So B intersection B, it will be equal to 5. Okay, so we are seeing what is the common area between this set and the area outside the circle. There is nothing common, so it is equal to 5. Okay, then we have A, this is a set and its intersection with empty set is in fact an empty set, which is equal to 5. A intersection B intersection 5, it will be 5, which is equal to RHS. Let A and B be two sets. Prove that A union B minus A is equal to A union B. Let us take the LHS again. So we have LHS is equal to, so we have A union B, minus is replaced by intersection, and A will be replaced by A complement. So here use distributive. So we have A union B, distributive property. Then we have intersection. Then we have A union A intersection. We have A union B intersection A union A complement. So let us see. This is A complement. The union of these two. Okay, the area which is in A and in A complement. So this will be equal to the universal set. Okay, this is equal to the universal set here. So let us denote universal set by this. Now we are being told A union B intersection universal set. So let us show it also here. Let us suppose this is A, this is B. Okay, so this is our, this is A union B. The outside region is the intersection. So since this whole region and this A union B region, it will be equal to, since this is the smaller set, universal set is bigger set, the intersection of smaller set and universal set, or the intersection of smaller set and bigger set is equal to the smaller set. It will be equal to A union B here. Okay, the intersection of smaller set with bigger set will be equal to the smaller set. Like if we, let us say we have B is a bigger set, A is the smaller set. Now if we take the intersection here, we will get B intersection A. It will come out to be A only. So which is equal to RHS. There are two things. Another, if we have the union, in case of union B union A, the union of bigger set with smaller set gives us the universal set. Show that A union B is equal to A intersection C implies A is equal to B. Okay, so to prove that A is equal to B, that is A and B are two equal sets, we need to prove that A is the subset of B and B is the subset of A. That is to say, let us suppose A is a set containing 1, 2 and 3. B is another set 1, 2 and 3. To prove that A is equal to B, what we need to do? We need to prove that A is the subset of B and B is the subset of A. Here you can see A is the subset of B and B is also subset of A. That means A and B are equal then. We need to prove that very thing. So let us suppose let X be an element that belongs to set A. Okay, if X is an element, let us suppose 2 is here, element which belongs to set A. That implies X will belong to A union B. Okay, since A is the subset of B, if X belongs to A X will belong to A union B. Okay, here what will be the A union B? Let us suppose here A union B will be in fact 1, 2, 3. Okay, this has nothing to do with the proof, so I'm just trying to show you here. Here you can see 2 belongs to A union B, which implies X will belong to A intersection B. That is being given us here. And here we can also see, let us see the intersection of A and B sets. So intersection will be again 1, 2, 3. Okay, so I am repeating, it is just to explain how do I getting these things here. Okay, this is nothing to do with the proof. Proof is still this thing. Okay, so if X belongs to A intersection B, it implies X belongs to A and X belongs to B. Okay, so if this is the case, it implies A is the subset of B. Okay, likewise, if we take this thing here, now we need to prove B is the subset of A. So let us suppose Y is an element that belongs to B. Okay, if Y belongs to B, that means Y will belong to A union B or B union A. That is commutative. Okay, union is commutative, which implies Y will belong to A intersection B or B intersection A, because intersection is also commutative. That is to say, A intersection B is equal to B intersection A, and A union B is equal to B union A. Okay, again, this is nothing to do with the proof. If this is the case, that implies Y will belong to A and Y belongs to B. Again, if Y belongs to A, Y belongs to B, that implies Y is the subset of, Y, that is B is the subset of A. Okay, so combining this result with this result, okay, from 1 and 2, what will we get? Since we got A is the subset of B and B is the subset of A, which implies A and B are equal. So let A, B and C be 3 sets such that A union B is equal to A union C and A intersection B is equal to A intersection C. Show that B is equal to C. So what we do here, so we take this statement, so we have, let me see, I have space here. So A union B is equal to A union C. I take this statement again here, that is, let me write it here, A union B is equal to A union C. Now in the first case, what I do, I take B intersection on both sides. Okay, so I take B intersection here, here also. In the second case, I take C intersection on both sides, C intersection, C intersection. So it is like multiplying both sides by 2. Okay, this intersection side. So let us solve it here. So we have B intersection A using distributive property, then we have union B intersection B is equal to, here also we have B intersection A union B intersection C. So let us first solve this one, then we will solve this. So B intersection A can be written as A intersection B by commutative property, that is 2 into 3 is equal to 3 into 2. It is the same thing. That is B intersection A is equal to A intersection B. Then we have union B intersection, the intersection of a set with itself is the set itself, so it will be B here. On this side, let us write it like this, A intersection B union B intersection C. Now A intersection B union B, the union of smaller set with the bigger set is in fact the bigger set. Let me explain it here. Let us suppose this is set A, this is set B, and this circle is, this lens shaped circle is our A intersection B. Now the union of this lens shaped figure with circle B, with set B, here you can see, the union of this I-shaped circle, I-shaped region with this whole region, it will be equal to set B. So we can write it here, B is equal to A intersection B union B intersection C. Now let us solve this side. So here we have C intersection A union C intersection B is equal to C intersection A union C intersection C. Okay, using distributive property. So it can be written as C intersection A is A intersection C, commutative property. Then we have union here. This can be written as B union C. Likewise, we can write it here A intersection C union. This intersection of a set with itself is the set itself. So here we have A intersection C union B. So I have done the mistake here, so it is intersection. We have intersection here. Again, the union of smaller set with the bigger set is in fact a bigger set, as I have explained it here. So we have set A, set C. This is A intersection C. This whole region is C. So the union of smaller set with bigger set is the bigger set. So here we will get C is equal to C. So here we have A intersection B. Here we have A intersection C. But we are being given that A intersection B is equal to A intersection C. So can I write in this place as A intersection B union B intersection C is equal to C. So why I have written it here? Let us suppose this is equation 1 and this is equation 2. Now here you can see we have, or if I rewrite it, so let me rewrite it like this: C is equal to A intersection B union B intersection C. Okay, so let us suppose this is second equation. From 1 and 2nd, since RHS of the two equations is same, we can equate LHS. That means B will be equal to C. Okay, that was our question. Show that B is equal to C. Let us take another question. The question is, let A and B be set such that A intersection X is equal to B intersection X is equal to phi, and A union X is equal to B union X. Show that two sets are equal. That is, set A is equal to set B. Okay, so what we do here? Let us take this statement. We are being told, and let me write it here. We have the A union X is equal to B union X. And let us take it on this side also. So we have A union X is equal to B union X. What we gonna do? Let us take the intersection. So we have two things here. Let us take A intersection on both sides. So we have A intersection here, A intersection here, and on this side let us take B intersection on both sides. Okay, now we have A. So using distributive property, we have A intersection A union A intersection X is equal to, so likewise here we have A intersection B union A intersection X. Okay, now solving this, so the intersection of a set with itself is the set union A intersection X is equal to, so we have here A intersection B, so A intersection B we don't know, union A intersection X. Now here we have A union, we are being told A intersection X is equal to B intersection X, which is equal to phi. So A intersection X is equal to phi, so this is phi here should be equal to A intersection B union A intersection X, we know it is phi. Now the union of smaller set with bigger set is always the bigger set, so phi is the smaller set, A is the bigger set, so A union phi will be A is equal to, again here the union of smaller set with bigger set is the bigger set itself, so here we will get A intersection B. Okay, so let us solve this one. Again, so B intersection A, we have B intersection A union B intersection X is equal to B intersection B union B intersection X. Now here, using the commutative property, we can write A intersection B union. Now B intersection X, that's being given as phi. That is being given as phi is equal to, so the intersection of a set with itself is the set itself. Union, we have B intersection X, again B intersection X is phi. So here we write phi. Now the union of smaller set with bigger set is always bigger set. So we get here A intersection B is equal to the union of smaller set with bigger set is the bigger set. Okay. Now let us see what we got. So A intersection B is equal to A intersection B is equal to B. So let us suppose this is equation first, this is second, from 1 and 2 since, or let us rewrite it here, make right left hand side or right hand side same. So this can be written like this: A intersection B is equal to A. From 1 and 2, since left hand side is same, we can equate the origins. It implies set A will be equal to set B here. Let us take some word problems on sets. The question is, in a school there are 20 teachers who teach math and science. Out of them, 12 teach math and 4 teach both math and science. How many teach only science? We are supposed to find out. Okay, so let us see what we have been given. We will also explain it with the Venn diagram. We are being told total number of teachers is equal to 20. That means number of teachers, that is, who teach math union science. This will denote our total number of teachers, which is equal to 20 here. Okay, we are also being told out of them 12 teach math. Number of teachers who teach math, it is being given us here 4, or rather 12, it is being given 12. And number of teachers who teach both math and science, that is being given us who teach both math and science, it is equal to 4. Okay, we are supposed to find out the number of teachers who only teach math. Okay, so the number of teachers who teach only science. The question is, who teach only science. So for that, what we do, let us use our formula that we have got earlier. So we know that N math union S, it will be equal to number of teachers who teach math plus number of teachers who teach science minus the number of students who teach math, teachers who teach math and science. Okay, so total we have been given 20. Number of teachers who teach math is 12 plus number of teachers who teach science, we are supposed to find it first, minus the number of teachers who teach math and science, that is being given us here 4. So number of teachers who teach science will be equal to, so 12 minus 4 is 8, so 12 minus 8 is 12. So number of teachers who teach science is 12, but we are supposed to find out the number of teachers who teach only science. Okay, now for that, number of teachers who teach only science, that will be equal to number of teachers who teach science minus the number of teachers who teach math. So S minus M, we know this formula also. That will be equal to the number of teachers who teach science minus the number of teachers who teach both science and math and science, which will be equal to, so here we have 12 minus both teach 4, so only who teach science will be equal to 12 minus 4, which is equal to 8. Now how do I show it on the graph, rather on the Venn diagram? Let us suppose we have two sets here. Okay, let us suppose this set denotes the teachers who teach math, this set denotes the teachers who teach science. Now number of math union science, so the number of A math union science will be number of teachers who teach math plus number of teachers who teach science minus the common area. Okay, so this is M union S. The shaded part, so the area inside the circles is our M union S. We were being told number of teachers who teach math, that's 12. So this whole region, it is equal to 12. Okay, that is 12. number of teachers who teach math and science. So this common area, this is our number of teachers who teach math and science. Okay, and this is equal to 12 who teach math. So who teach both math and science, it is 4. The question was to find out this area, the number of teachers who teach only science. So who teach only science will be this very area. So carefully see. To find out this area, this this green area, what we need to do, we need to find out the number of teachers who teach science. So this whole circle denotes, red circle, it denotes the number of teachers who teach science, and we calculated it as number of teachers who teach science, it is equal to 12. Now if this whole circle is equal to 12 and we are supposed to find out the number of teachers who teach only science, okay, so number of teachers who teach only science, so from this circle, because this circle represents the teachers who teach science, from this we subtract this very thing, okay, that is the number of teachers who teach only science, it will be equal to this whole S minus M. Now this S minus M will be equal to number of teachers who teach science, so this, from this we subtract this common area and we know it is equal to M intersection S. Okay, so this will give us, this shaded part will be equal to 12. Sorry, it will be equal to this whole circle, which is 12, minus the common area, which is 4, which is equal to 8. So this is how we show it on the Venn diagram. How to explain the set question using Venn diagram. In a school, there are 20 teachers who teach math and science. Out of them, 12 teach math and 4 teach both math and science. How many teach only science? Okay, so the information that we have two sets. Let us suppose this is set A, represents the teachers who teach math, and set B, the teachers who teach science. Now the union of math and science, it is 20. So total number of teachers is 20. We know this. The area of these two circles is 20. Now number of teachers who teach math is 12. So this whole circle denotes the number of teachers who teach math. Number of teachers who teach math and science. So this common area between the circles, it is number of teachers who teach both math and science, it is 4. We are being told to find out the number of teachers who teach only science. Okay, so how do we find it out here? Since the area of this whole area of the two circles is equal to 20, we have 20 total number of teachers. Here we can see this circle represents number of teachers who teach math, and this lens-shaped circle denotes the teachers who teach both math and science. Then number of teachers who teach only math will be this very area. Okay, so it is 12 minus 4. So number of teachers who teach only math, it will be this very region. Now we know that both math and science, it is 4. Okay, since we know the area of the circle, two circles, is equal to 20, because we have 20 teachers here, that means if the whole area is 20, so we have 8 plus 12. So what will be this? So as we get it equal to 20, so 8 plus 4 is 12. 12 plus 8 will be equal to 20. Okay, so what will be this area? This area will represent the teachers who teach only science. Okay, so this area will represent the teachers who teach only science. Okay, now this said, this whole circle will denote the number of teachers who teach science. So we can also find out that very thing. So that will be equal to 8 plus 4, which is equal to 12. Okay, so total number of teachers who teach science will be 12. Total number of teachers who teach only science, that will be equal to the number of teachers who teach science minus the number of teachers who teach both math and science. So here, since we are being told only science, it will be equal to 8. Now let us solve the question using Venn diagram. In a town of 1,000 families, it was found that 40% families buy newspaper A, 20% families buy newspaper B, and 10% buy newspaper C. 5% families buy newspaper A and B, 3% buy B and C, and 4% buy A and C. If 2% families buy all 3 newspapers, find the number of families who buy only A newspaper, only B newspaper, or none of the newspapers. Okay, So let us see. Let us suppose this black circle denotes the number of families who buy newspaper A. Okay. And here we are being told that number of families who buy newspaper A, it is 40%. 1000 total families, total number of families is 1000. So this whole rectangle denotes our universal set. That is, we have total 1000 families here. Okay. Now out of these 1000, 40% buy newspaper A. So 40% of 1000 is 400. So this circle denotes the number of families who buy newspaper A. Okay. Then we are being told 20% families buy newspaper B. So number of families who buy newspaper B, it is 20%. So 20% of 1000 is 200. And let us denote the circle B. So this circle, this B, it denotes the families who buy newspaper B. Okay, this is being given. Also, we are being told that 10% buy newspaper C. That is, number of families who buy newspaper C, it is equal to 10. 10% of 1000 is 100. Okay, so let us draw circle C also here. Okay, so let me try to draw the circle C. So this red circle denotes the families who buy newspaper C, and number of families who buy newspaper C is 100. That's been given us. Now we are also being told that 5% families buy newspaper A and B. That is, number of families who buy newspaper A and B, it is 5%. 5% of 1000 is 50. That is, newspaper A, newspaper B. So this region denotes our, what we call, the number of families who buy both newspaper A and B. So it is, how many are there? 50. Okay, so let us give number of, here we have A is equal to 400. Number of families who buy only B newspaper, it is 200. Number of families who buy newspaper C, it is 100. Now number of families who buy newspaper A and B, so this circle, this lens shaped circle, so its area is 50. So I don't have to say 50. So this whole area, okay, it is 50 here, who buy both A and B. Also we are being told that 3% buy B and C. So number of families who buy B newspaper and C newspaper, it is 3%. 3% is 30. So B and C, so this area, let us denote it by, so this is 30 here. Also 4% buy A and C. So number of families who buy A and C newspaper, it is being given us as 4% of 1000 is 40. So this area between A and C, so this is the common area between A and C, so its area is 40. So don't get confused. This 40 is not this very triangular looking shape. It is the area of, this is the common region. Okay, I cannot show all the things on this because I have the limited space or limited constraints in terms of colors and how to present it on the tabletop video. Okay, also we are being told a number of families who buy all the 3 newspapers, it is 2%. That is number of families who buy newspaper A and B and C, it is 3% minus 30. Now the question, so this area which is common to all the 3 circles, it is 30. Okay, now what we are supposed to find out, we need to find out the number of families who buy only A. Okay, so what is the region there denotes the number of families who buy only A? So this will be this very region. Okay, this will be, it will denote the families who buy only A newspaper. So it will be equal to, so number of families who buy only A, it will be equal to then this whole circle, we know that this whole circle is 400. From this we subtract this region first. Okay, since we need to find out this thing, so we need to find out, subtract this thing here, so which is 50 here, the comma region. Then we subtract this thing, which is 40 here. Now when we subtract these two, we need to, okay, I guess I have done a mistake here. So 2% families by all three, so it is 20 here. Okay, it is 20 here, 20 here. Now when I subtract this region, then this region, now this region is subtracted, it gets double counted, so I have to subtract this, I have to add this here. Okay, so it will be equal to 400 minus 50, so we have 90, which is 310, plus 20, which is 330. So 330 will be the families who buy only newspaper A. I hope you are getting what I am trying to say it here. So if this whole circle, so from this whole circle, when we subtract this thing, and then when we subtract this thing, then we have to add this thing because it gets double counted here. Okay, that's why I have written plus 20. So I am showing you. So there is, as you know, formula here, but using Venn diagram, it looks easy to solve them. Rather, it is easy to solve using the Venn diagram because it saves a lot of time here. Now, can you tell me the number of families who buy only B newspaper? Again, so this whole blue circle, it is 200. Okay, remember what I am trying to explain. So this whole denotes 200. Only B will be this very region. Okay, from this circle, I will subtract first this length. Okay, 50. Then I will subtract this length, which is 30. When I subtract these two lenses, then I have to add this 20 because it gets double counted. So only B will be equal to, so 200 minus 80 is 120. 120 plus 20, I guess it is 140. Sorry if I cannot do the calculation right. Okay. Likewise, if we were told to find out the number of families who buy only C newspaper, so since it is not in the question, but we can also find out that very stuff here. So only C will be this area, so it will be equal to only C newspaper. It will be equal to whole circle, so number of families who buy newspaper C, which is 100, minus, then we have to subtract this length and this length and this smaller one, then add the smaller one. So from this we subtract 40, the number of families who buy A and C, minus this 30, the number of families who buy B and C, and then I have to add the number of families who buy all A, B and C. Why? When I subtract this thing, I am taking this into account. Likewise, when I am subtracting this thing, I am taking this account. So I have to add this 20, okay, to get rid of the overlapping. So it will be equal to 100 minus 40 minus 30. 30 minus 20, which will be equal to 10, I guess. Okay. We are also being told to find out the number of families who does not buy any newspaper at all. Okay. Since we know that 400 families buy newspaper A, 200 buy newspaper B, 100 buy newspaper C. This region, because this region denotes 1000. From 1000 we subtract these three. That is, if I have the space here, so who don't buy at all, none, that will be equal to total number of families minus number of families who buy A union B union C. Or simply, since we have 200 here, so 1000, there are 1000 families. From this we subtract the number of families who buy newspaper A who buy newspaper, subtract B, and who buy newspaper, C. So 1000, so it is 4 plus 2 plus 1 is 700. So 1000 minus 700 will give us 300. So 300 are those families who do not buy any newspaper. That is this very area outside the circles. Let us take another question on sets and solve it using Venn diagram. The question is, in a survey of 25 students, it was found that 15 students had taken subject M, 12 had taken subject P, 11 had taken subject C, 5 had taken M and C, 9 had taken M and P, 4 had taken P and C, and 3 had taken all 3 subjects. Find the number of students who had taken only C subject, only M subject, only P, P and C but not M, M and P but not C, only one subject, at least one of the subjects, and none of the subjects. Okay, this is the information. And let us draw the Venn diagram first. Okay, we will be explaining all this stuff using Venn diagram this time. So let me show. So this whole rectangular region, it is equal to 25 students, because we have the number of students is 25. Okay, so let us draw this circle, and let us assume that this circle represents the number of students who have taken only M subject. So number of students who have taken only M subject, this is represented by this circle, and it is equal to 15. Okay, likewise let us take another circle and let us denote it by P. So P is the number of students who have taken this circle represents the number of students who have taken P subject, and it is equal to P is equal to 12. And let us take another one this time, number of students who have taken C subject, and let us denote it by another circle. Okay, this circle represents the number of students who have taken C subject, and it is equal to 11. Okay, we are also being told the number of students who have taken M and C, which is equal to 5. So 5 have taken M and C. Number of students who have taken M and C. Let us see here. So this is M, this is C. So M and C will be this very region. The region enclosed by this blue arc and black arc, and it is being told it is equal to 5. Okay. Likewise, number of students who have taken M and P. So M and P, this very region is common to M and P. The region enclosed by this red arc and black arc, and it is 9. Okay, number of students who have taken P and C. P and C, what is the area? This very region P and C, which is common to them, enclosed by this red and blue. So its area is total 4. Also we are being told 3 had taken all 3 subjects. That is number of students who have taken M and P and C, it is 3. So this arc enclosed by blue, black and red, it is 3 here. Okay, this we know. Now let us try to find out first, and let me first find out the number of students who have taken P and C but not M. Who have taken P and C but not M. Now let us find out the region which is common to P and C but not M. Okay, so I guess this very region enclosed by black, this blue and this red, this will be the region which is common to P and C but not M. So number of students who have taken P and C subject but not M subject. We know that this whole region, it is there lies 4 students, and this region has 3. So the remaining region will be 4 minus 3, which is equal to 1. So number of students who have taken P and C but not M, P and C but not M, it will be only 1 student. Okay. Number of students who have taken M and P but not C, M and P but not C. Now M and P is this very region, it is equal to 9. From this we subtract this region. So 9 minus 3 is 6. Okay. Number of students who have taken M and P but not C. So this region is common to M and P but not C. So since the area of this whole region is 9, from this we subtract this region, which is 3. 9 minus 3 is 6. Okay. Now let's also find out the number of students who have taken M and C but not P. Okay, so let us find out M and P but not sorry, M and C but not P. M and C but not P. This we got as 6. Now the area which is common to M and C but not P, that will be this very region. Since this whole region is equal to 5, from this we subtract this region, so 5 minus 3 will be 2. Number of students who have taken, M subject and C subject but not P subject, so this is the region. Okay, it is 2. Now we need to find out the number of students who have, okay, now let's solve this one. Since we got this information, number of students who have taken only C subject. So where is C? C is this whole blue circle. From this, since we need to find out only C, so this very region denotes the number of students who have taken only C subject. Okay, so what will be the area of this very region? It will be the area of whole region minus this area, and this area. Since the area of whole region is 11, so from 11 we subtract 1, 3 and 2. Let's get 5, so it will be 5. So number of students who have taken only C, it is 5. Number of students who have taken M. Okay, so since this whole black region denotes M and it is equal to 15, from this we subtract this very region. Rather, from this whole we subtract these individual regions. So 15, so we have to subtract from 15 6, 3 and 2. So it will be 4, I guess. Okay, so it will be 4. Number of students who have taken only P. So only P, since this red circle denotes P, it is 12. From 12 we subtract 6, 3 and 1. 12 minus 10 is 2. So this is 2 here. So this is 2 here. This is in fact 2. Having said that, number of students who have taken at least one of the subjects. Number of students who have taken at least one of. By at least one we mean, what we mean, either they have taken subject M, or they have taken subject P, or they have taken subject C, or they have taken M and P, or P and C, or all the subjects. Okay, so that will be equal to this whole region, 4 plus 6 at least. So we need to find out the at least. So by at least what we mean, either the person has taken student this M subject or P subject or C subject, or M and C, or C and P, or all. Okay, so that will be equal to these all individual areas. So it will be equal to 6 plus 2 so that will be 23 students who have taken something. Okay, either 1 or 2 or 3 or at least 1. Okay, sorry, my bad. We need to find out the number of students who have only taken one subject. Okay, sorry for this mistake. Now only one subject means this very region. Number of students who have taken only C subject, this very region. Number of students who have taken only P subject, M subject. So that will be equal to 5 plus 4 plus 5 plus 2 is 7. Only students who have taken only one subject, that will be equal to 4 plus 2 plus 5, that will be 11. Now number of students who have taken at least one of the subjects, that means they have either taken M or P or C, or both M and P, or M and C, or P and C, or all subjects. So that will be this individual, adding the individual part. So that will be equal to sorry, so that will be equal to 23. Who have taken at least one of the subjects is 23. Now the number of students who have taken none of the subjects, since we have 25. Okay, 25 students, and at least one subject is taken by 23. So 25 minus 23, that is 2 students will be those who have taken none of the subjects. That is this very region, the region outside the 3 circles. It is equal to 2. Okay, I hope I make myself clear and you found out this series helpful. Please share, subscribe this channel so that it will become useful for other persons also. Okay, so I take these questions or topics free of cost. I don't charge a single penny. Okay, keep shining and stay blessed.